In this video, I'm going to go over how to do light calculations with the electromagnetic spectrum. So the electromagnetic spectrum is a spectrum of electromagnetic waves, which are waves that carry energy. They can travel through any medium, through space, and yes, we have them ranked, not ranked, but they go in order on the spectrum from, and it depends on the spectrum you look at, but this side is shortest wavelength to longest wavelength, which also means highest frequency on gamma ray side to radio waves that have the lowest frequency. And energy is directly related to frequency, so gamma rays have the most energy down to radio waves that have the lowest energy. And you can determine, if I give you the wavelength, you can find the frequency or the energy of a wave based off of two equations that we're going to go through really fast. So these are the two equations. If you need to pause this video to write them down, please do so. Our first equation is C equals, that's lambda times frequency. C is the speed of light in a vacuum. We'll only do calculations with speed of light in a vacuum, but if the medium changes to be air, water, whatever, C can change, but we're just using this. So 3 times 10 to the 8 meters per second. That is always C. F is frequency of the wave. Frequency is measured in hertz or 1/second. They're the same thing. You might also see S to the -1. That's all a correct hertz unit. And then wavelength, which is this symbol, is measured in meters. You might not always get a wavelength value in meters. You might be given it in, I don't know, nanometers, millimeters, but to use this formula, wavelength has to be in meters because speed of light is meters per second. The other equation is the energy of a wave. E equals h, which is a constant, Planck's constant, Max Planck, times the frequency of the wave, and that h is always this value. So let's get started. What's the frequency of a wave that has a wavelength of 428 nanometers? So I've been given wavelength. That is the symbol for wavelength, 428 nanometers. I want to find my frequency. Looking at my two equations, I'm going to use this one because that one has wavelength and frequency. So wavelength times frequency equals C, which is 3 times 10 to the 8 meters per second. And this is the equation. Now we can't just go jump into this formula because wavelength is in nanometers and it needs to be in meters. So I'm going to erase this. There's a conversion that you probably want to jot down. 1 meter equals 1 times 10 to the 9 nanometers. Nanometers are super small compared to meters. So there's a lot of nanometers in 1 meter. And so we're going to use that conversion in dimensional analysis to change nanometers to meters. So 428 nanometers times, this is nanometers here, which means at the bottom it has to be nanometers. That many nanometers are in 1 meter. If you go type that into your calculator, you should get 4.28 times 10 to the -7 meters. That's our wavelength value. I'm going to erase all of this. And now we're ready to plug in to our equation. So our equation is C equals wavelength times frequency. C being the speed of light, 3 times 10 to the 8 equals my wavelength, 4.28 times 10 to the -7 times its frequency. I'm trying to solve for frequency, so we'll divide each side by 4.28 times 10 to the -7 to cancel it out. Now go ahead, pause the video, and try to type this in. I want you to make sure you're typing it in correct because of negative exponents, scientific notation, that can be tricky. And when you type it in, you should get the frequency equals 7.01 times 10 to the 14 hertz. So that's how we use that first equation. Next problem. How much energy does a wave carry that has a frequency of 2.34 times 10 to the 12? So F, my frequency, 2.34 times 10 to the 12 hertz. I'm looking for energy. And so for this problem, I'm going to use the E equation, which is H times F. So H, again, is that constant, 6.63 times 10 to the negative 34 joules per second. There's no conversion needed with this one because hertz is the right unit and H is a constant, so that's the right unit. So we can just plug this in. So energy equals H, 6.63 times 10 to the negative 34 times the frequency, 2.34 times 10 to the 12. And again, pause the video, please type this in to make sure you're typing it into the calculator correct. And you should get an energy value of 1.48 times 10 to the negative 21 joules. Now this might seem like a really small number, because it is, but when we talk about energy, we're talking about how much energy one wave is carrying. So it's always going to be small. Even the energy value for gamma rays will be a negative exponent in small because it's one wave. Frequency should always be a positive exponent up here, and the energy will always be negative, so that can a negative exponent, so that you can kind of check yourself to see if you're doing your math correct. And then we're going to solve for this problem, which combines both equations. So how much energy does a wave with a wavelength of 450 nanometers carry? So I'm looking for energy, which means I'm going to have to use energy equals H times F. I know H is 6.63 times 10 to the negative 34 joules per second, but I don't know my F. So that's a problem, but I did give you the wavelength. Wavelength 450 nanometers. So we can use our first equation, C equals wavelength times frequency, because we know what C is, 3 times 10 to the 8 meters per second. We can use this equation first and solve for F. Once we get F, we can plug it into this equation and solve for our energy value. And that's what we're going to have to do. Now I'm going to need to erase this because our wavelength is not in the correct unit. It's in nanometers. We want it to be in meters. So 450 nanometers times, in that conversion again, 1 meter has 1 times 10 to the 9 nanometers. That ends up equaling 4.5 times 10 to the negative 7 meters. Now that wavelength is in the correct unit, let's solve for frequency. C equals wavelength times frequency. 3 times 10 to the 8 equals my wavelength, 4.5 times 10 to the negative 7 times frequency. We're going to divide each side by 4.5 times 10 to the negative 7. And when you do that, we should get a frequency of 6.67 times 10 to the 14. Now that I know my frequency, I can plug into my energy value. And I want you to go ahead, pause the video, and plug that into the energy value and see what you get. And you should end up getting energy equals 4.42 times 10 to the negative 19, and the unit for energy is joule, which is a capital J. So that's how we use these equations to solve for light problems. I hope this helped you learn how to plug them in and do the math.